so not only is it hard to express with rewards what we want, sometimes we can't even say what we actually wanted, and it's environment dependent, right? So you actually have to know what your learner is going to be learning about before you can decide what reward to assign to things. So that's problematic. So we've been looking at ways of actually just saying what you mean, right? Telling the agent, well, raw rewards are a terrible programming language for people to use because they're indirect and input dependent. So maybe you should go the other way. Maybe what we should do is have people specify behavior. Oh, you want it to go and get to the goal without touching the blue? Thank you, that's all you have to say. And then we have an automatic procedure for generating rewards from that, so that the rewards will actually encourage the agent to do the thing that the agent does well, which is, even in a stochastic environment, even with lots of different influences from different places, I'm going to maximize the reward. And because this reward came through this process, maximizing that reward is going to cause the agent to do what I wanted it to do. So how would that look? It's changing from, okay, I want it to go to orange and avoid blue, so I have to say orange +1, blue -4, and that's what the agent gets. I want to switch that to just, say what you mean. So how can we say what we mean? How can we say what's in our hearts? Logic, obviously. Logic is a way of expressing specific kinds of desired outcomes. And we've been starting to look at linear temporal logic. This has been used in the planning and reinforcement learning community a bit. A number of years ago, Bacchus, Pavir, and Grove showed that you can actually specify reward functions as linear temporal logic expressions that then decide for you which reward value you want to deliver. So we're kind of building on that same idea. So what is linear temporal logic? If you don't know, I don't know if you know, but I didn't know, but now I know, so I'm going to tell you. You get the regular logic operators and or not on, say, features of the world. But then you also, in addition to those, get temporal operators that you can talk about things about the trajectory. And so there's a whole raft of these things. But the three that I'm going to focus on are I want to say the most common ones, because they're on the slide the whole time. Eventually, which is a diamond shape. Always, which is a square shape. And then strong until, which is a funny looking U. Strong until being, well, I'll just define them in context. So having these operators at your disposal actually makes it pretty reasonable to say what rewards you want for a bunch of standard reinforcement learning MVP type environments. So the examples that I've got up here at the moment, so one kind of classic problem is like mountain car. Mountain car says, you should, I keep hitting the same spot over and over again. You should, you're driving a car, you're powering it up and down, you want to get to the goal location. So eventually achieve the top of the hill. Okay? So diamond P, eventually P. I want that to happen. You can also express avoidance type goals, like a pole balancing sort of thing that says, always don't drop the pole. Right? So always is the square, and then not Q. If Q corresponds to the pole being flopped over one side or the other, then always not Q says, keep the pole balanced. The grid world that I was showing before can be specified using this until operator, which basically says, I want you to avoid blue until you get to red, or I want you to avoid the bad state until you get to the good state. Okay. And you can say more complicated things as well, things that people have said like, this is the taxi problem. In the taxi problem, you have to drive the taxi over, pick up a passenger, drop the passenger off. I can say that too. I can say, eventually, I want you to pick up the passenger, and then from there, eventually drop off the passenger. And so now the compositionality of the language starts to be really powerful. It lets you say things about sequence, which would otherwise be very, very difficult to express as just plain reward. What people will tend to do, and maybe you're thinking this too, is that you augment the state space. So you add something to the state space saying, well, I've already picked up the passenger, so I don't have to do that again. And I just put my rewards on this augmented state space. Ultimately, this is going to be that idea. But like, you don't have to design the state space. You should just say what you want, and that state space should come out. So in the case of the taxi problem here, yeah, I guess that's. Oh, but what I wanted to point out is that this is a different expression than, for example, eventually P and eventually Q, which says you need to pick up the passenger and you need to drop off the passenger. So you can do them in the other order if you want. Right? This is actually enforcing the idea that no, you have to pick up the passenger first. All right, so good. So this gives you a flavor. There's a bunch of other things. If you put eventually and always together, you get something nice. You put always and eventually the other way, you get something nice. It's a pretty cool language. And so we can sort of say, great, why don't we just use that and be done with it? It turns out that linear temporal logic and learning don't go together nicely at all. And the reason, there's a bunch of reasons for this, but this I think is the simplest way to explain it. So imagine that this is our whole environment. The agent being one of these three states. This is a trapped state. From this state, this is the agent never make B true again. This is another trapped state. For the B state, the state that's blue, it has two actions it can take. One results in a self-transition. It stays in that state with some low probability it actually transitions to a trapped state. And the other one, same thing, except we don't know what those probabilities are. In the learning setting, we actually have to discover those probabilities. Which is not so bad. We do this in reinforcement learning all the time. We actually put nice bounds on how quickly we can learn the probabilities with sufficient accuracy that we can almost optimize for word. But you can't do that with LTL. So LTL, imagine that the thing that we're asking it to optimize is always B, always blue. So what's the right action for the agent to take? Well, it turns out it depends critically on these probability values. If B1 is 0, no, sorry. If this is 0, 1 minus B1 is 0. B1 is 1, then taking the X action would allow the agent to stay in blue indefinitely. But even the tiniest little error in that will mean that eventually it's going to fall out of the blue state and get trapped, and therefore always won't be true. So, well, maybe the other action will do it. Well, again, you have the same problem with that. So which action you pick, X or Y, depends on having a perfect approximation of those probabilities. Not even any error in it whatsoever. The smallest amount of error can result in completely not the right thing being optimized. So our answer to that has been that the problem is infinity, right? The problem with these temporal operators are, this needs to be true not till the sun burns out, but like the real forever. And that turns out to be really hard to reason about or get agents to actually do. So instead, what we're going to do is let those operators still mean what they mean, but they're only going to have to hold over a finite window. Once the operator expires, it no longer has any influence on our behavior, the agent's behavior. So in particular, we can say stuff like, eventually mu p, and that says that p has to be achieved sometime, for that to be true, for that to be satisfied. P has to be achieved in the next k time steps, where k is drawn from a geometric distribution with parameter mu. And so the idea is that eventually this thing expires, so you're going to have to get around to actually doing it, or you lose, or else you haven't actually satisfied the expression. It's now a stochastic thing, which I imagine won't make the logical model checking people super happy, but it does at least get this sort of notion that there's a time scale over which I need this to hold true. And beyond that, whatever, that's then, this is now. Same trick on each of these operators. So, and in fact, always is actually not, eventually not P, which is kind of neat. It's sort of, there's like a De Morgan's law of temporal operators. And we can do the same thing with until. So you have to achieve P in the next K steps, while Q is true the entire time. So Q until P equals true. So this is kind of cool. All the examples that I showed you, if we just give it a parameter and we can express the sort of thing that we want. The agent now, what it needs to do is behave in such a way as to maximize satisfaction. So maximize the probability that not only would the environment do the things that you are needing it to do, but the specification will as well. And this gives us a way of actually dealing with both kinds of those uncertainties. So we're in the process of trying to finish this idea up, but this talk was kind of the motivation for getting this story to go. The way that this would be used then is we have some environment that the agent's going to be in, and either in a reinforcement learning setting where the agent doesn't know the environment, or a planning setting maybe where it does. But the behavior, the way that I'm going to specify the behavior is I'm going to write one of these formulas down. That formula induces a little MDP, a little specification MDP, that is just the states that you need to be able to interpret whether or not you've actually satisfied the formula. So if it has a sequence thing in it, you're going to have a state that keeps track of whether you did the first thing in the sequence, you're going to have a state that keeps track of whether you did the second thing in the sequence. That is the task. Then the cross product of the task and the environment give you the MDP that the agent actually needs to solve. It's set up in such a way so that maximizing the probability of satisfaction, maximizing reward in that composite MVP causes the agent to actually satisfy the formula in that MVP. And we don't need to know in advance exactly what the environment looks like. We don't need to know what the slip probability is. We just give it the task specification. They get put together and planning happens. So this is what happens if we do this for the example. You can see it in the bottom left corner there. Not B until R. Right? Don't touch B until you get to red. Don't touch blue until you get to red. So here it is, like doing its darndest. In spite of the fact that it's slipping every once in a while, it's still making the best effort it can to get to the goal. And in fact, it would have made all the right sort of trade-offs. If there was another path that was longer, but has the property that it's much less likely that you can bump into a puddle because it's sort of a drier area, it would have made the right kind of utility theoretic trade-offs between those two things, but we got to tell it what it is that we actually wanted it to do. I'm just going to give one last example of this for Charles' benefit, because he really likes this example. He says it has something to do with somebody's life, but he didn't tell me exactly who it was. It's the procrastination problem. And the procrastination problem looks like this. You want to occasionally read Reddit, which are the blue squares here, but eventually graduate. Okay? You want to get through and get your PhD, but you don't want to just grind it out every day. You're allowed to go and look at Reddit, and blow off some steam. But the thing is, if you do that for long enough, then you won't graduate. So you have to somehow manage to balance these two things. In standard reward language, you can't quite do that, in the sense that if you give no reward for Reddit, then Reddit won't get read, which maybe is okay. But again, for the purpose of the example, that's not ideal. Or you can give a little bonus for Reddit, and if you make that bonus a little bit too big, then it's going to read Reddit forever and never graduate. And I think we can all agree that that would be a shame. So we can actually tell it what we want it to do in this geometric version of LTL, and with something that looks like this. Eventually, and then eventually holds over, let's say, the next 1,000 time steps. So I have to give it a sense of the temporal window. So roughly, 1 over 1 minus 0.999 steps. Achieve red, and it should always be the case over the next smaller window that you eventually have some red. Okay? That operator will eventually expire, and then the agent, we'll call it Charles for no good reason, will actually go on and graduate. So this is what the behavior actually looks like in this case. It started up, it's like, yeah, read it. Oh no, I really better graduate, and then it goes on. All right. So again, you may feel some kinship to that example, or you may not. We don't need to say more about it. But this is work that's currently underway, and we're trying to understand how these different discount factors interact, whether it's necessary for the agent to know that the clock's expired. Right at the moment, it gets to see, oh wait, no, Reddit's not rewarding to me anymore, I'm going to move on. LTL is definitely more friendly than rewards, I want to say. I guess I don't have user studies that prove that. Hard to imagine not being able to prove that. But even LTL is not super user friendly, right? So Charles and I spent hours kind of arguing over, no, the and should be an or, wait, the until should be before the never. And so it's actually, I guess I'm not that good at LTL, partly, but it's not completely intuitively obvious to the end user. So maybe there's other ways of kind of getting that same idea out. I sort of pointed this out indirectly, but when you combine the controller, the task specification with the environment, it blows up the size of the state space. So each of the task states gets an entire copy of the full environment. So the planning problem, which was already really hard, gets much, much harder. Are there ways that we could actually approximate, like encourage the right kind of behavior with a lot fewer states than that? And we think there's ways of doing that, but we haven't really made that very formal yet. And this also this can be maybe accomplished by using different discount factors for different reward sources. So that Reddit, the enjoyability of Reddit decays a lot faster than the enjoyability of Reddit. All right, so that's kind of the end of the piece where I'm going to talk about programming reward functions. And now I'm going to talk about other ways that we can get reward functions into agents so that the goals that we have are eventually taken on by the agent. So the first one I want to talk about is inverse reinforcement learning. So the idea in inverse reinforcement learning is this. So I have a behavior in mind. There's something I want the agent to do, and that agent needs to be encouraged via a reward function. But I don't know how to talk reward function. So what I'm going to do instead is say, let me show you, right? Let me demonstrate me doing the task really well. I'm taking actions and I'm maximizing reward, and see, can't you do that too? And so in inverse reinforcement learning, it tries to infer the rewards that would motivate that particular kind of demonstration, that particular kind of behavior. So the way I like to think about it, some people ask, well, why is it inverse reinforcement learning? I can make it inverse reinforcement learning. So if we think of reinforcement learning as being a block that combines input from what the rewards are and what the environment is to generate behavior, then inverse reinforcement learning flips that around, and the behavior and the environment come in and the rewards come in. What's cool about having the rewards come out is that once you have a representation of the task in a reward function, then I can drop the agent in a different environment, or maybe a related environment, or have it solve problems that it hasn't seen before because it knows what's good and what's bad and how to do it. So here's a concrete example to get you to think about it. Because I think IRL is really neat, and it's been having very positive influence, but I think it's a little bit underappreciated because it is a really powerful concept. So we're gonna have you do a little inverse reinforcement learning. So this is a grid world, just like all the other grid worlds, except now there's orange and green, so it's really a completely different grid world. You're going to be moving through the grid, and in fact, here's what I want you to do. I want you to do this kind of behavior. So this is me demonstrating the behavior. So now if I give you a different grid with the colors arranged in a different way, and I tell you, okay, well the colors are, each color is either an attractive square or an aversive square, or maybe it's just a neutral square, it's just decoration. Can you figure out which squares are which from demonstrations? Actually, can you figure out from just this one demonstration? What can you figure out from just this one demonstration? So green is good. Excellent. All right. Blue? Probably bad, right? So it's following the shortest path to green. But, suspiciously, it's the shortest path that kind of weaves through the blues. So we don't know for sure whether it just happened to take that particular path. We're actively avoiding blues. But, my bet's on that's not so good. What about orange? We don't really know much about orange. But red is either good or neutral, right? How do we know that? It's not through what the agent did, but in a sense it's what the agent didn't do. Because the agent really didn't like red. If red was something aversive that it should be avoiding, then it wouldn't have taken this path. There's other paths it could have taken. And so that kind of contraindication, that's the word, this sort of idea of arguing from what didn't happen is a really powerful thing that people seem to do all the time, and these agents can do as well to learn things about other things in the environment. It doesn't have to be shown negative examples of lots of different things to know that they're bad. You can see one positive example of something else to say, I guess you were avoiding that. So we can actually run, using Berlac, we can run inverse reinforcement learning, a particular kind of inverse reinforcement learning algorithm that I worked on called maximum likelihood inverse reinforcement learning that specifically runs gradient descent or gradient ascent on the parameters of the reward function to try to maximize the probability of the observed trajectories. So what it does in this particular case is it says, okay, well, that particular path, we can make that more likely by assuming that blues were being avoided, because it was a path that avoided blues. It needs to assume that the white squares are neutral. It needs to assume that the blue square, actually, it was green in the other way. The green square is attractive, because that otherwise doesn't really explain very well why we took that particular path. And it's interesting. It actually turned out to think that this orange bar is a little bit aversive, and I'm guessing it probably did that because we could have gone along that strip and we didn't. We crossed it in just one place. It's not great evidence, so we'd have to probably see a lot more examples to really believe it. But it kind of is leaning in the direction maybe that's not a good thing. And then the red is almost completely ignorable. It's like, nah, you didn't go around that. It doesn't make the trajectory more likely. It doesn't help explain the trajectory to say that red is being avoided. It also doesn't help to say that red is being attracted to, because why didn't it just stop it? So, I don't know. I find this to be a particularly enlightening way of looking at this problem because, if you just say, find your reward function for which this would be an optimal policy, you get degeneracy. And so the policy the reward function where everything has 0, that's a perfectly reasonable optimal strategy. But it doesn't really explain it as well as something that says, oh, actually it's trying to avoid these and go to these. All right, so on the topic of generalizing these kinds of reward functions, again, it's using the fact that we told that, okay, all the blue squares are kind of the same. So it's generalizing across them. There's other kinds of representations that allow for even more powerful generalization. So one particular representation that I've been working on and is implemented in Berlin, and James did a lot of work on it in his dissertation, is object-oriented MVPs. The idea of saying the state of an MVP actually consists of a bunch of objects, and objects have attributes. So in this particular picture, there's a robot and some rooms and door and a block. The robot is in some particular XY coordinate. The block is also in some particular XY coordinate, but it also has a particular color and shape associated with it, and so on. We can have various propositional functions that can give us relational information about what's happening to these objects. So block 1 is blue, room 2 is red, that sort of thing. And that lets us be able to write tasks in a way that's fairly environmental independent. So in this particular one, if I wanted to say something like, move the chair to the green room, I can write that as a logical expression of the form, well, block in room B are, whereas block is blue, block B is blue, and room R is green. And so if I told the agent that I want you to bring about the state of affairs so that this becomes true, it can do that, and the way it'll do that is by actually moving the chair into the room. So we've been using this idea in the context of actually saying what you mean, like using English to specify a reward function. In the following sense, we have an algorithm that takes a data set, sort of like supervised learning, but it's not so supervised in the sense that we give it a whole bunch of English expressions, English commands, and then the trajectories that should be followed for each of them. So if I tell you, take the yellow backpack to the green room, I want you to do this kind of path. If I tell you to take the red chair to the green room, I want you to take this kind of path. If I want you to go to the blue room, I want you to take this kind of path. And then we run this same kind of maximum likelihood inverse reinforcement learning sort of idea, but on a much more complicated generative model that includes not just how the rewards influence the behavior, but how the rewards influence the words. Right? So the words are being generated by the intention. And so we can do reasoning in this generative model, and actually we trained it up from data that we got from people on Turk, and it would end up following the kinds of commands that it was given, 75% accuracy, 73% accuracy, and we could reuse that same mapping to actually have robots do stuff in the real world, not just agents crawling around. So what it's doing under the hood is it's actually trying to figure out, okay, these are the words, this is the behavior. The thing that needs to explain this is some kind of reward function representation that sits between those two. That it connects to the words, but it also connects to the behavior. And so when we run it on this, it actually starts to generate these sorts of representations, and it kind of learns the meaning of the words that the people use, at least grounded in terms of the propositional functions in the object-oriented MVP. All right, I want to give one last example, two last examples. Right, I'm starting to run out of time. Actually, I've been running out of time the whole time. So there's another kind of way of looking at this problem that I want to talk about that a couple people worked on that I think is also really neat and promising. And this is the idea of viewing the design of a reward function as itself a kind of optimization problem. So imagine that I can actually specify whether a behavior is good or not. I can make some kind of a scoring function for that, make a fit function for that. So that's kind of what I had in mind. What I tell is if I tell the system an implementation of that fit function, then what the system is going to try to do is it's going to have the agent learn in environments of the kind that we wanted to ultimately learn in with different reward functions. And it's going to see which reward functions do the best job at inducing the desired behavior. So it's doing sort of what we would do if we were sitting at the keyboard and like, okay, I want to, I should probably give a little less penalty for blue. I should probably give a little more penalty for green. It's just sort of doing that behind the scenes automatically based on our specification of the kind of behavior that we want. And sometimes that actually turns out to be a really powerful way of doing things. So some work by Singh, Lewis, Bardo, and Sword looked at this question in a simple grid world domain and actually showed that the reward function that just did what the task was, which in this case is you're supposed to go over to a box, open the box, eat whatever pops out of the box. I don't know where they live, but that's a good idea. But they wanted the agent to learn that, to actually go to a closed box, open the box, and eat what pops out. And what they found is that they literally gave that fitness function to the agent as a reward function. It did okay, but not as good as if you actually give it a slightly different reward function. And what they found is roughly get some reward for eating, that's great, but you also get some reward just for opening boxes. Right? It's like, that's kind of a nice thing unto itself. That's not the optimal, that doesn't induce the optimal behavior because the agent kind of likes opening boxes a little bit too much. But it makes learning a lot faster because it wanders around the world and opens up a box like, hey, that was kind of cool. And I'm going to get really good at opening boxes. This is great. Hey, when I open boxes, food jumps out. I should eat that. And so it actually causes it to be in the part of the state space where it can learn much more efficiently. We're doing some work in a multi-agent setting that's an awful lot like that, where essentially, I'll give you all the details of it. Roughly what happens is the agents are involved in a kind of cooperative, competitive kind of task. One agent tries to steal from the other agent has to decide whether to punish that transgression or not. And what we found is that agents that involve a sense of enjoying revenge, that's like taking it back out on the other player, ended up much better for everybody for them to have that kind of built in. Even though that wasn't really what they should have been optimizing. The punishing actually was injurious to the agents, but like, still, having to do it when it's the right thing, you just have to do it. It's a dish that's best served in terms of reward functions. Then the whole system actually ended up being better by deviating from the real rewards. And then super briefly, another way that we can actually convey task information to the agents is by giving rewards ourselves. Just like in the cat training example, we can give +1s and -1s to the agents ourselves. And there's been various work, and we have some work that complements that, that we've discovered that, in fact, people don't give rewards that should be optimized. Like, if you literally optimize the rewards that people give you, it confuses the heck out of learning algorithms. Instead, you actually need to use the rewards as evidence of whether or not the agent has the right reward function or not. So that's the way that we're looking at it. So the agent is learning in a way that says, if it gets a positive, then that means the thing that it was trying to do may have been what you wanted it to try to do. So the agent is actually reasoning about the reward function that's in the trainer's head, as opposed to literally just trying to maximize the rewards happen. Why? Well, in part because it turns out that people will very often introduce positive reward cycles. Like, this is good, and that's bad, and the agent says, that's not that bad. So I can do the good thing twice and get the bad thing once, and still end up making a profit. That's not what we wanted it to do at all. We wanted it to just not do the bad thing. And so using the negative as evidence against the bad thing seems to be much more effective. We've run a number of user studies where we have people training little cartoon dogs in various ways. And we look at the kind of training patterns that they do, and actually they vary quite a bit. It turns out to be really useful to not just try to guess what reward function the trainer has in mind, but also to guess how they're translating that into rewards. That process itself turns out to be important to avoid positive reward cycles and the like. And just to wrap up. All right, so here's what I was trying to argue, that rewards are a powerful way to shape agent behavior in complex environments because it really lets you deal with various kinds of uncertainty really effectively. To do this, it's helpful to separate your concerns, separate the reward and the task, and find better rewards than maybe the literal rewards that define the task. And I talked about programming, demonstration, evolution, and using people's input as ways of actually getting that information to build the reward function. I think a key direction for future work is that there's so much more to programming than just, not writing an assembler, right? Because that's essentially what we're saying here, is that reward functions are kind of like assembly language for agents. And an assembly language is really hard to write. We need to pop up a level and be able to abstract away a bit. But there's so many ideas that have been discovered in the field of software engineering. If we could bring those to bear for specifying how agents should behave, that could be a very powerful idea. And one last Burlap plug, that's where you can download it from burlap.cs.brown.edu. Thank you so much for listening. Sorry for going over.
Questions?
You were assuming that the states and transitions were given. Sorry, you were assuming, in case you can't hear me, that the states and transitions were given, and so you got to play with the rewards. Well, why is it obvious in a lot of cases, like the problems don't necessarily come packaged up with states and transitions? And it seems to me like, at least in principle, you might want to play with the states and transitions as well as the rewards.
Good. So of all the different things that make up the MVP, why focus on the rewards as something that is a way for the person to express to the system how they want the system to behave. You're absolutely right. And in fact, playing with the state representation is actually one of the most powerful ways of getting agents to do what we want. I want to say that some of that can be learned, and we don't need the person to actually say those things. But I think it's complementary with the stuff that I've talked about. I don't think they're at odds really at all. And I think Charles would actually agree that playing with state representation is actually, and action representation is critical when you're trying to apply these ideas to real tasks.